KNC provides transformative education to young women, leading to the growth of the nation. This institution lies in the front line of accredited colleges of Delhi University by NAC from 2016. KNC has been selected as a mentor institution by University Grants Commission under the Paramarsh UGC scheme for mentoring NAC accreditation aspirant institutions to promote quality assurance in higher education. The past few years have been a real challenge at every level, including health, smooth functioning of college, teaching and learning, and college maintenance. Kamala Nehru College has turned these challenges into opportunities to innovate, create, and extend ourselves in its best possible capacity. As I begin with, freedom of mind and knowledge is the real freedom. Our college is celebrating Azadi Ka Amrit Mahotsav, a 75-week grand celebration launched by Honorable Prime Minister Shri Narendra Modi, independence. To honor this occasion, we, the Department of Mathematics, have organized Mathophilia 2022, an annual mathematics day themed on Azadi Ka Amrit Mahotsav. Mathematics gives us hope that every problem has a solution. The Department of Mathematics leaves no stone unturned to make the students ready to face the challenges of life and make us confident that every lock in our lives comes with a key. Our teachers always aim to achieve excellence in teaching and research, developing more interest and curiosity in us towards mathematics. Our department encourages us to always look beyond the book of numbers and equations and enhance ourselves by participating in co-curricular activities. The annual department newsletter Axiom enables our content writers and editors to promote the experience and creativity. We are starting an event with the inaugural lecture by Professor Pratulananada, INSC Teacher Awardee. We have various interesting games and events lined up for you all to participate in. The first event for the day is Quizibus, the ultimate quiz competition, followed by Kalai Maths, which is a Rangoli competition based on the theme Azadi Ka Amrit Mahotsav. We can't wait more to see your amazing Rangolis. Then we have another event called Meme It, Win It. With the IPL fever spreading all over us, it would be fun to giggle over some memes made by our very creative participants. Last but not the least, FILOMAT, the photography competition, the lens to the text. For an amazing day ahead. Remember, both will happen. What is not acceptable is good. I wish good luck to all the participants. May the best one. Over to Tanya.
Thank you. Harshita, let's wait for Professor to join in and then we'll start with the welcome speech. Thank you, Ishika and Soumya.
Thank you, ma'am.
दिव्या मैम सर आ गए हैं, मैं सर को एडिट कर रहा हूँ।
Okay.
Good morning, sir. It's Harshit from Mathematics Department, Kamala Nehru College.
Good morning. Yeah.
The study of mathematics, like the Nile, begins in minuteness.
Tanya, just a while, just a while. Sir, do we clearly audible to you? Hello. Hello.
You're audible, Harshit sir.
Pratul sir.
Yeah. Yes, you are audible.
Sir, just with a few introduction of few seconds, then you can start your lecture. You know, the coordinating team.
I will start about Okay.
Tanya, let's start now.
Good morning.
The study
will
of
start at
mathematics,
around
like the Nile.
exactly 9:30. Yeah.
Okay.
Okay, sir. Okay, sir.
Tanya?
The study of mathematics, like the Nile, begins in minuteness but ends in magnificence. I, Tanya Singh, greet you all on behalf of Mathematics Department, Kamala Nehru College. Maths is delightful, but sometimes this can be hard to see and even harder to convey to students, isn't it? This lecture would amplify the wonders of mathematics. Moving forward with Anvita.
A very glorious morning to our prestigious audience. I, Anvita Agrawal, feel highly privileged to welcome our eminent guest of the event, Professor Pratulananada, Professor of Mathematics in Jadavpur University, Calcutta. He has earned more than 19 years of teaching experience, with a glorious period of 16 years in the research field of mathematics. His domain of specialization is pure mathematics, mainly in set-theoretic and general topology, analysis, sequences, and summability theory. He is currently holding the eminent position of Editorial Board Member in reputed journals like FILOMAT, AFRIKA MATHEMATIKA, Applied General Topology, and Journal of Mathematical Analysis, Kosovo. Sir holds the life membership of many prestigious mathematical societies. He has contributed so many research publications with numerous national and international renowned research scholars in several reputed journals, which has multiple citations. His precious knowledge, experience, and achievements are innumerable enough that I fall short of words. His detailed research on these significant concepts has paved an insight for our generation to have more interest and knowledge about the undiscovered theories of pure mathematics. We are really fortunate that an excellent researcher like Professor Pratulananada Das has graced us with his presence. Today, he will be speaking on the topic ideals and the natural density function, particularly understanding the sets of natural numbers. Again, we convey our warm welcome to him and request him to enlighten us with his speech. Thank you, sir.
Okay. So. Yeah. Okay, so thank you very much for the invitation. Though we have, you all know, we have now offline classes going on, so full classes going on. So it has been a little hard for me. So I'm not also prepared that much well. So yeah, okay. So the forget about the title. Okay, so what we will, since the audience, it seems that the audience is very mixed from the UG first year to UG third year, something like this. So we will not go into too much mathematical details or something like that. Okay, so we will have, how I should put it, we will have a sense of history, how, so a particular notion, how it came into being, and at least I will mention some of the very big results in mathematics which evolved from that particular notion. Okay, and very briefly, how people then moved forward with some more abstraction. Okay, so we start by, okay, so historically what happened is, let us talk about, so our primary objects are natural numbers, so let us start with them. So natural numbers are also called counting numbers, no? Because we use them to count objects, and it has nothing to do with mathematics. So people who do not have any formal education in mathematics, or everyone know what are, say, 1, 2, 3, 4, these things everybody know. Okay? So historically what had happened, you all know that in the very ancient times, when people did not know how to count, then they started the process of counting, because it was in their life. Okay, so for example, 10 people from cave are going for hunting. Now they will go for hunting in different directions in the day, and by the night they will come back. So in order to know that everyone has actually come back, what they would do, they would put, would put let's say an object, let's say a stick for each of the person who is going for hunting. So if 10 people are going for hunting, then they would put 10 sticks, and when one by one they come back, they would take away the sticks. And so they now know that if all the 10 sticks are exhausted, then this means that no one is in the jungle, and everyone has come back. But the problem is when they have, say, 9 sticks exhausted but 1 stick remaining, then they know that someone is still in the jungle and he has not come back. So they would go to search for him. So this is how counting process started. So same thing to count, say, the fruits, they are taking fruits from somewhere. So to count the fruits, to distribute the fruits among themselves. Okay. So these counting numbers were there for, okay, almost from the start of the human civilization. Okay. Okay. But as we can understand that they did not understand what are the large counting numbers. So the counting numbers, definitely, because they, for example, they could not say count the number of leaves in a tree. If there is a big tree, the number of leaves, it is not possible for them to count. So they had the idea of natural numbers as counting numbers, but the numbers were very small. Okay. Okay. So then the formal, in that sense, discussion of numbers came up in when in the later stages when civilizations came into being in different parts of the world. So particularly we can just look into one civilization, that is the Greek civilization. Because in general we start from there. In India also at the same time, and actually before that we already had the concepts of numbers and their how I should put it, their algebraic operations, and even the concept of zero. Okay, so in the Greek civilization still there was no concept of zero, but in India actually there was a concept of zero. Okay, in any case, so we start with say the ancient Greek civilization. So in the Greek civilization, what they so for counting numbers, they had actually they had two processes. Okay, so one is concept of magnitude and one is concept of number. Okay, so in that time they were actually different. Okay, so the concept of magnitude is something like that. It refers to the length of a geometrical line, and the concept of number is thought of composed of just units. Okay, so at the time there was only one number, one concept of number, which is now known as whole number. Okay, so for example, Pythagoras seems to have thought that he actually in his book it is written that all is number. So what he meant by that is that so Pythagoras would have thought that one, so I will always throw my fingers, so 1, 2, 3, 4, so which we now know as natural numbers, but it as a geometrical way, but not as lengths of line, but rather points on the line. So if I have the real line, then Pythagoras thought them as points. So 1 is here, at a distance of 1, this is another point, it is 2, 3, 4, in this way. Okay, so first came in this particular notion of numbers, points. So we can understand that addition, subtraction and multiplication of integers or natural numbers or counting numbers were natural concepts, because if I have 3 points and we have 2 points, if we add them, then we have 5 points. Okay, similarly, if I have 5 points and I take away 2 points, then I have 3 points. Okay, and multiplication is nothing but addition. So just how this, in the same way we just explain things to the preschool students, that I have the 3 boxes of apples, each containing 5 apples, then 3 into 5 is nothing but I just add all the apples in the 3 boxes, so I have 15 apples. Okay, so addition, subtraction, multiplication were there, but there was no notion of division, because when we are looking at points, then it does not make any sense. So there was no notion of division, though there was a notion of divisor. The divisor, actually there was the name was it was known as submultiple. Okay, so for example, we know that 3 into 4 is 12. So in that time they will say that 3 and 4 are sub-multiples of 12. They would not say that 3 or 4 divides 12 because the concept of division was not there. Okay. So after Pythagoras, what happened is that then came Euclid, and whatever mathematics we even now deal with, in some sense the groundwork has been from the start of Euclid. So Euclid actually thought natural numbers as magnitude. So that is the difference. So he thought it is a magnitude. So what he did is that if I have something like a unit magnitude, so I will specify certain length and we will call it 1. Then if on a long line, or so in a long line, if I have say 5 units consecutive, then I will say that particular length corresponds to the number 5. So when this notion of magnitude came, then people thought that okay, we can now think of the operation of division. Okay, so then division was defined and correspondingly ratios were defined. Okay, so if I have 2 magnitudes, so suppose I have 2 sticks with I have 2 sticks, so I can just think about the ratio between the 2 sticks. Okay, because when division is possible, I can always think of the ratio. Okay, so what I want to how I should put it? So what I want to say is that so always so at that time there were mathematicians were primarily philosophers. Okay, so people tried to think about more deeply about what we have and what we can do more with it, and what are some natural questions that come into our mind and how we can give answers to those questions. Okay, so what Euclid was one of the how it is universally accepted is that Euclid is one of the greatest mathematicians because he had developed he had written some 10 or something more books, and in those books he had been different mathematical formulas and mathematical notions, and particularly from Euclid, what happened is that there was some logical argument, and so the mathematics was there, but the treatment was not rigorous. So he first thought that there should be a rigor in the thinking process. So if I want to prove something, then this means that I have some conditions are given, and what we know with the help of those knowledge, we will argue our truth to the conclusion. So it became more rigorous. Okay. So so we should be very grateful to that great mathematician Euclid, because he particularly gave those rigorous treatments. Okay. In ancient India also there were, so at around same time there were some very, very fine mathematicians who also gave the same type of rigorous treatments to mathematics, but somehow maybe due to the Western, since Western influence or whatever I will say, somehow the Indian history of mathematics is well known, but not that much well known. Okay, but one thing we should credit Euclid, that the amount of rigor that he had given to the ideas, probably in India or there was a very good group of mathematicians in Egypt, and there were some, there were other civilizations also. So that much rigor was not there. We should be truthful about that. Concepts were there, many outstanding results were there, but in general, that rigor of Euclid was missing. So Euclid was the one who first thought that actually he was thinking about real numbers. So at that time there was nothing called real numbers. So natural numbers, for natural numbers he introduced the notions of ratio and what I have said, that using the notion of magnitudes. And when he thought and introduced the notion of ratio, automatically the concept of rational numbers came. Okay? And when rational numbers came, then famous, so it is again a very famous example. It was also it is also in Indian context also, irrational number, particularly root 2 came up. That so how root 2 came up, that so if a square with each of the lengths of the sides unit is drawn out, and then we set that, we go the diagonal, and then if we just draw a circle with the diagonal as the radius, then this circle will cut the x-axis at that time, because Euclid already had the notion of geometry, x-axis, y-axis. Each point on the plane has a unique position corresponding to the two coordinates. So he had already developed them. So this circle will cut the x-axis at a point. Now what happened is that he wanted to, so when I am saying about Euclid, it in some sense Euclid and the fellow mathematicians, there were also very good philosophers and mathematicians just alongside him and just after him. Okay. So they all tried to understand what is the length of that particular magnitude from the point 0 to that point where the circle has cut the x-axis, and they came to the conclusion that this magnitude cannot be measured. So why? Because at the time, what was the how people used to measure is something like this, that I take a small unit, and from the point 0 I will place that unit side by side, and so if my unit is say 1/10, so if I place it say 20 times, I will reach at the point at the magnitude of 2, something like this. If I have a unit 1/100, then I have to place it 200 times side by side to reach at the point 2. Okay. So what happened is that whatever small unit they were taking, when they were going forward towards that particular point where x is, we know now x is equal to root 2, always that particular point will be inside. So after some steps, I will have a point which is on the left hand side of root 2, and when we add one more unit, I will just cross one. I will cross that root 2. So I will never reach at the point root 2. Okay. So in this way, they understood that there are numbers which are not necessarily rational numbers, leave alone whole numbers. So the concept of irrational numbers came up. Okay. Okay. So this state of, so this was the state of how I put it, mathematics, particularly the state of numbers for a long time, almost 2000 years. Okay. And after that, again, one by one, some mathematicians tried to again go back and regroup the things and see what are these things. Okay. And so now coming to nature. So after that, what happened is that after a lot of years, the staving, so something, historically it happened something like this, that in 1970s, Stavin first thought of about decimal expansion of a number, and then the irrational numbers came into existence, and we now all know that it was formally defined in some sense by two mathematicians. One is Cauchy and one is Dedekind. Okay, so Dedekind formally defined real numbers through Dedekind's cut, and Cauchy had actually defined. Cauchy had particularly for Cauchy actually did not define the real numbers, but he actually gave one of the most important tools to define real number, that is Cauchy sequence. Okay, so now we all know, those who have already done a course in sequence know that any Cauchy sequence of rational numbers, if we take all the Cauchy sequence of rational numbers, then they are convergent to some real number, and in this way all the real numbers will be exhausted. So the method, it is not very obvious, but so I will not go into any definition of sequence or etc. So those who have done a course in sequence series already, so they would know that what is a Cauchy sequence, and so every real number can be thought of as the limit of a, so there is, so if we consider collection of all Cauchy sequences, then they can be made into some groups, classes, and in each class, so actually an equivalence relation can be defined, and it will just partition the whole system into equivalence disjoint, pairwise disjoint equivalence classes, and to each equivalence class we actually it corresponds to a real number. So then it became much more clearer. Okay. Now about natural numbers. So in the same time, so people actually, there were two different opinions about natural numbers. For example, there were some mathematicians like Kronecker, who told that we should not define natural numbers. What is a natural number? So there is a famous quote of Kronecker that God, if I God God gave us natural numbers, then everything is made by man. It was something like that. So there were many mathematicians who did not want to define natural numbers because they said that okay, it is from very ancient times. What we know what are natural numbers, so we do not have to give it a formal definition. Okay. And on the other hand, there were some mathematicians who tried to define natural numbers. And one of the most eminent mathematician and whose approach actually still I have forgotten whether it is still taught in the undergraduate syllabus. So Peano's axiom. So Peano had given certain axioms to define natural numbers. Okay, so very briefly speaking, what Peano's axioms? What were Peano's axioms? So I am speaking just very briefly, not all of them. So something like this, that except, so every natural number for Peano, 0 is also a natural number. So he started from 0, 1, 2, 3. So he was thinking about this set 0, 1, 2, 3, 4, 5. So this. So one of the main axioms were that every natural number should have a successor, and every natural number except 0 should have a predecessor. And if I have two elements whose successors are same, then those two elements should be equal. And finally, in some sense, the mathematical induction that if some property, if a set contains 0, and it has the property that if it contains a natural number n, then it will contain also n plus 1, its successor actually. So the successor is denoted, if for a natural number n, the successor denoted by Sn is equal to n plus 1. It is denoted by n plus 1. So if I have a subset of the set of natural numbers which contains 0, and for if it contains n, then it always contains n plus 1, then it will be equal to the set of natural numbers. So broadly, very briefly speaking, so these are called Peano's axioms. Okay, so in this way, Peano had defined natural numbers, and so it was one of the major formal definition of natural numbers. And okay, so after this I will go into, okay, I will present. Okay, so let me, okay, so 1 minute. Oh, why I am unable to go. Yes, so okay, so just 1 minute. Window. Okay, so is it visible? Okay, so
Yes, sir. Yes, sir. It's visible.
it is visible. Okay. So because for the next section, I need to use the board. Okay, so in this way, so you see that so over more than 2000 years, this number system was developed, and after piano actions, people had more clarity about natural numbers, obviously. And okay, so now then came the notion of cardinality. So okay, what is happening? Yes, cardinality. Okay. So what is cardinality? So suppose I have a set of real numbers and I have another set of real numbers. We are only dealing with real numbers. Then if I have a mapping from A to B, we will not define a mapping. You all probably know what is a mapping. So what are the main two concepts which are actually useful is that F is called injective, F is injective, or it is also called one-to-one. When different elements have distinct elements have distinct images. So X not equal to Y implies Fx not equal to Fy. So distinct elements have distinct images. Okay. So clearly, if I have an injective mapping from the set A, so if I just draw, this is the set A and this is the set B, then this means that I have also, whenever there is a mapping, this means that for every element in the set A, I have a corresponding image here. So if there is X, there is Fx, always every element has an image. And so what does injective means? This means that distinct elements have distinct images. So in some sense, the number of elements in the set B should be always greater or equal to the number of elements in the set A, because otherwise it will not happen. And the next definition is that F is called surjective, or it is called onto, when for every Y belonging to B, there exists a X belonging to A such that Fx is equal to Y. So every element has a pre-image. So here if I take a point Y, then always whatever may be the Y in B, I can go back and here is some element in the set A where there is an element X whose image is Y. Okay, and this is true for all Y belonging to B. So this means that in some sense the number of elements in the set A should be greater or equal to the number of elements in the set B. And if the mapping is both injective and surjective, then it is called a bijective mapping. And a bijective mapping means that, so technically this means that the number of elements in both the sets A and B are equal. And we say that the sets A and B have the same cardinality. So if there exists exists a bijective mapping. So if there is a bijective map that is injective plus surjective, then bijective map from A to B, then we say that so we will just write very so we say that, so we will write in this way that cardinality of A is equal to cardinality of okay. So now just try. So you know what is a finite set. So now we come to the set of natural numbers. Okay. So there are two types of subsets of natural numbers. Okay. One collection is finite set of natural numbers. Actually, the definition of a finite set in general is that a set is called finite if there is a bijection map from that set to an initial segment of the set of natural numbers. Initial segment means that 0, 1, 2 up to some particular natural number. So if I have a set which has say 10 elements, then I can put a bijection from that set containing 10 elements to the initial segment 0, 1, 2, 3 up to 9. Okay. So every finite, so in this way finite sets are defined, and there is a result already. So finite sets are characterized by the property that a finite set cannot be equivalent, that is, there is no bijection between a finite set and any of its subset. Okay. And so just taking the contrapositive argument, infinite sets are defined. So a set is called infinite only if there is at least one subset of that set A which is equivalent to that particular set. That is, there is a bijective mapping from a proper subset of that set to the set A. So in this way, infinite sets are defined. So now we want to understand N. So N is an infinite set. So we start with, so I write down 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, it is N. Okay. So let us write down the collection of all even integers. So for brevity, I write it 2n. Okay. So what is 2n? 0, 2, 4, 6, 8, 10, 12, 14, 16. Okay. Now let us write for brevity the collection of all squares. Okay, let us write it as n squares. Just it is not a notation, but I am using it as just a notation. Okay. So what will be 0, then 1, then 4, then 9, then 16, 25, 36, 49, 64. So okay. Now look at these three sets: the whole natural number set, the collection of all even integers, collection of all square numbers. Okay. Now see the sets. It is, as I have drawn the sets exactly, it is evident that there is a bijection mapping from them. So my bijection mappings are n to 2n. The bijection mapping is that n is so here. So here n is going to 2n. So with respect to this mapping, this is a bijective mapping from capital N to 2n. So this means that n and 2n have the same cardinality. Similarly, n is going to n square. This is again a bijection. So this means that all the sets have the same cardinality. So 2n and n square, they are infinite subsets of the set of natural numbers, but they have the same cardinality. Okay, so in some sense it is so. If I want to measure a set of natural numbers, so cardinality is the basic tool to measure the size of a set. But the problem here is that though so all the three sets have the same cardinality, fine, but when we are looking at them from the geometrical point of view, they are not looking same. No, so on the natural line, the capital N is the whole set. When we are considering this 2n, the set of all even integers, then I can see that there is a gap. There is a uniform gap between all the elements, and the gap is bigger than the usual gap that is happening for the set of natural numbers. And if we see these set n square, here it is more, we actually will get a little bit more perplexed, because here there is one gap, but as we are going on the right hand side, the gap is increasing. So the gap is increasing. Okay, so as we go on the right hand side of the natural line, the gap between any two integers from the set n square, this is actually increasing. So the elements are becoming more, so elements are with the gap, elements are becoming scarce and scarce. Okay, so definitely these three sets should not be bracketed, so should not be put in the same bracket. Okay, so here comes the notion of natural density. So here comes the notion of natural density. Okay, sorry. So natural density. So what is natural density? So natural density is defined in this way. So I take a set of natural numbers, and what we do is that we take this set. Let us write 0 to n minus 1, because in my case, capital N, I am writing from 0 to, okay, and I divide it by n and take the cardinality of this set. Okay, so what does that mean? This means that I have a set of natural numbers A. I am looking at the initial segment of the set of natural numbers 0 to n minus 1. In this 0 to n minus 1, I am looking how many elements of this initial segment are inside the set A. How many, exactly how many elements. So if, for example, for the above three sets, for example, if I look at the three sets, and if I yes, somewhere, let us write n, say n, let us write, say, okay, let us write 64. For example, let us take n as 65, okay, n65, let us take n65, okay. So for the first set, so if my A is the set of all natural numbers, then the upper portion is 65, and it is okay, 64, sorry, 0 to n minus 1, so sorry, 64 by 64. Here it is up to 64, there will be 32. So the last element will be, so since so 32 by 64, and here it is up to 64. See that there are 1, 2, 3, 4, 8 elements. So 8 by 64. So now see that I am actually, if I consider this particular ratio, then I am getting a little better understanding about the three sets. For the first set, the collection of all natural numbers, the ratio is equal to 1. For the set of even integers, it is going exactly as our intuition that this ratio is half. And for the set of all square numbers, it is actually 1 by n. Okay. So exactly. So this particular, so what, how natural density is defined is that, so this particular ratios are taken. So I should write n minus 1, sorry. So these particular ratios are taken for every n, and then we take, now I have to define the, okay, so for the next results we need sequences. So just listen, those who have already have a course on sequence, fine, otherwise just listen to it. Okay, so what we do is that we take the lim sup of these numbers, and this is denoted by d bar a, and similarly this is lim inf, and this is again the same thing, cardinality of a intersection 0 n minus 1 divided by n minus 1. Okay. Now those who have already had a course in sequence, you know that, look at this particular ratio. This ratio is always bounded by 0 and 1. So this is a sequence of rational numbers, actually fractions, sequence of fractions which is bounded below by 0 and bounded above by 1. So always the lim sup, that is the maximum possible, so the greatest limit point of that sequence, a cluster point, we should say cluster point. So the greatest limit point, the cluster point, and the list of the cluster points, they always exist. So this upper, so this is d upper bar is called the upper natural density, and d lower bar is called the lower natural density. So for any set A, these two always exist. Okay. And if I have for some set A these as equal, then we say that the set A has natural density and the natural density exists. And if I just, I am not going into the example again. So if I now just think about the three sets of natural numbers we had considered, it is now clear that the set of natural numbers itself, its density is 1. the set of all even integers, its density is half, and the set of all square numbers, its density is 0. And this shows that now, so see that now I have a tool which can actually differentiate between the infinite subsets of n. So from our geometrical point of view, we were quite sure that these three sets should not be of the same kind, but the cardinality was not sufficient to understand the difference between the three sets. But this, the natural density function, it was established, actually the definition came into being in the 21st century to understand this type of sets in the set of natural numbers, and particularly when people were working in number theory, arithmetic number theory, and then this definition came up to understand between the difference between different types of sets of natural numbers. So in particular, if a set A has density 0, then we say that A is small. So in particular, sets which have natural density 0, they are thought of as very small sets of natural numbers. And obviously, if a set has density 1, then it is thought of as a large set. So it is quite clear that if a set A has density 0, then its complement will be have density 1, vice versa. So, and the sets like 2n or 2n minus 1, the set of odd integers, or there are many sets like this. So if 0 less than dA, so if a set A has density greater than 0, then we generally say that we just say that A is not small. So not necessarily a large set. Large set means that its density should be equal to 1. But if the density is greater than 0, then we say that it is a not small set. Okay. So now let me, so there is not much time. Okay. So this is the definition of natural density. And then let me tell you at least three. I will not write these results. So let me tell you some. Okay. So before that, let us look at it to one more. For example, okay. Before that, so particularly these sets have been very interesting for the number theorists. Okay. So number theorists try to understand if a set is not small, what will be its properties. Particularly, there was a conjecture by one of the greatest mathematicians of 21st century, Paul Erdos. So Paul Erdos conjectured that when a set has natural density, positive natural density, so dA is greater than 0, then whether it will contain arithmetic progressions. You all know what are arithmetic progressions. So a plus n, a plus 2n, a plus 3n, so for some n. Okay. So if it goes up to a plus kn, so then we say that arithmetic progression of length k. Okay. So Erdos' conjecture was that if a set has positive natural density, then whether it will contain sufficiently big arithmetic progressions, or at least some arithmetic progressions. Okay, and this was solved by Endre Zemeredev, an Hungarian mathematician. He showed that if a set has positive natural density, then it will contain infinitely many, infinitely many arithmetic progressions of any arbitrary length. So the result was, obviously, the result was outstanding. And for this particular observation, he is a number theorist, and he proved a lot of results, very the influential, original, and path-breaking results. But for this particular observation, he was given the Abel Prize. Okay, so those who know about Abel Prize, those who do not know, Abel Prize is, in some sense, it is thought of as equivalent of Nobel Prize in mathematics. Since there is no Nobel Prize in mathematics, so for this, as Nobel Prize is given for the lifetime achievement. No? So Abel Prize is also given for the lifetime achievement, especially for some particularly very path-breaking results. So Zemeredev was given the Abel Prize for this particular observation. And the same observation was later proved. So his proof was very complicated. Okay, so the original proof must be about 100 pages or something or more. Okay, so it was very complicated, and later Hillel Frustenberg, an Israeli mathematician, he proved this same result, but using much more modern tools of mathematics, so, which come from ergodic theory and dynamical systems. So from ergodic theory, dynamical system proved this result. For that also, Frustenberg received the Abel Prize. So see, for just see the beginning of the problem, it is so simple, but the conjecture was so hard that almost nobody could solve it, and two people solved it, and both of them got Abel Prize. And then came the latest development. So if I talk about the collection of all prime numbers, you all know what are prime numbers. Okay, so now people wanted to first people wanted to think what is the density of prime numbers, because again the natural intuition tells us that as we move on the right hand side of the natural numbers, the prime numbers become scarce and scarce. So the distance between two consecutive prime numbers is getting larger and larger, in some, not always, but in general. So there is something called a prime counting function. So prime counting function tells us that for any positive integer n, here I am taking n as n is greater or equal to 1, I am taking the number of primes. Okay, it is called pi n. So the number of primes less than or equal to n. So the number of primes less than or equal to n, this is almost equivalent to n by log n. Okay, so this is called the prime counting function. And if we apply this, then it is now clear, since while taking the density of the set of a set, we are dividing this the number of elements less or equal to n by n. So this is actually giving me something like, so I should write limit n tends to infinity 1 by log n, and so this is 0. So the primes have natural density 0. So it was a very, in some sense expected, but a very unique result, which was proved only because of the notion of prime number, prime counting function was there. And then again the same conjecture was placed for the primes, that whether there are arithmetic progressions in the set of primes. And it was much later in 2000. So in 2002 to 2005, Terence Tao, you all probably know the name because he is one of the best mathematicians of this century and very prolific. And so Terence Tao along with Ben Green showed that even the set of prime numbers has arbitrary, so infinitely many arithmetic progressions of arbitrary lengths. Okay, and for that particular result, he received the Field Medal. Okay, you all know what is Field Medal. So it is Field Medal is given to someone whose age is less than 45. So below 45, and for the most path-breaking the result developed in those 4 years or last 8 years, something like this. Okay, so see that from the definition of natural density, so many things came up, and finally I will just. So if I look at the set of natural, so if I look at the set of natural numbers with density 0 particularly, then it is now clear that set of all natural numbers. So I am looking at the set of all natural numbers with density 0. So I am looking at something like this: A, for which dA is equal to 0, this collection. To see that it has 3 properties. 1, of course, n does not belong to this collection, so we write it as id. Of course, n does not belong to id. This is also from the definition of natural density. It is obvious that if A belongs to id and B is subset of A, then B belongs to id. Okay, so it is a hereditary class. So if a set has natural density 0, of course, all its subsets have natural density 0. And third is also quite simple observation, that if A and B belong to id, then their union again belongs to id, because this follows from the fact that the density for any two sets A and B, the density of A union B is always less or equal to density of A plus density of B. So if A and B are from id, so this means that density of A and density B are both 0. The right hand side is 0. So the density of A union B becomes 0. Okay. So the collection of all density 0 sets satisfies these 3 conditions. And also let us write fin. So fin means collection of all finite subsets of n. And from the definition of natural density, it is again clear that every finite set of natural number have density 0. So fin is subset of I. So the collection of all natural density 0 sets, which are perceived as small sets of natural numbers, satisfies these 3 properties. Additionally, this fin is subset of I. So this notion was later just generalized in this way that if I have a collection of subsets which exactly satisfies these three conditions and phi is subset of that collection, then it is called an ideal, and it is actually called a free or admissible ideal. Okay? So later what happened is that, so from set theoretic point of view, it happened that so the natural density is a number theoretic notion. So let me stop sharing. I do not need any more. Okay, so what happened is that, so the natural density is a number theoretic notion which there have been many research using this natural density, and then there have been different, it has many applications. There have been concepts of convergence, etc., using this natural density function which comes in the analysis. And in set theory, just using those three axioms of those three properties of the collection of natural density zero sets, if a collection of sets is thought of satisfying the same properties, then it is called an ideal. Okay, so in this way the notion of small sets can be generalized. So from the set of natural numbers, it can be generalized to any arbitrary set. And then a lot of work has been done and a lot of work still going on. But okay, I think I should stop here because, yeah, I do not have more time, and also I have classes after this. Okay.
So just for a few seconds, some of our audience has some questions, if you allow.
Yeah, just few, very few.
Those who have who want to ask some questions, then can ask now. Raj, I think.
Hello.
Yes, Raj, you are audible now.
Am I audible, sir?
Yes.
Yes.
First of all, thank you very much, sir, for a great talk. As you talk about the numbers and you talk about the causes sequence, then Chronicle says we don't need to define actually natural number. Then piano did it, and you talk about the density of natural numbers. So we study about the density in real number system also. So what is the difference between that real density which we studied in the real analysis?
No, yes, there is their density means yes,
Can we means my question is, can we relate means both the densities or something else like that?
in some sense you can know no, we cannot relate. No, because I think you are talking about. Are you talking about density? Means density in real line? You are talking about the notion
Yes,
of
yes,
denseness.
Yes.
Yes. No. We cannot talk about, because here the notion is not topological. It's not coming in topological way. It's just it is more coming from the geometrical point of view of numbers arising more with more gaps. So no.
Sir, one more question, sir. Is it the countability of natural number system which allow us to define such concept like natural density?
Yes, of course. So natural density, first thing, natural density is the most measured definition of density. But there are many other types of densities also. For example, you just told spoke about the set of real numbers. So there are also density defined for real numbers also. Okay. So, but those densities, so there are different, I should put it in this way, that there are different definitions of density functions there. Okay. Some of them, like natural density, are now well understood, and there have been a lot of work regarding them. But some of the densities, there is, for example, I am not telling, I have forgot the name. It is there is one density function which is in some sense becomes trivial, in the sense that with respect to that density function, every set has a density. Here, some set may not have a density. Okay, I have not given an explicit example here due to the time constraint, but there are sets of natural numbers which does not have any density. But there are some types of density for which density of any set is it can be defined. Okay. Secondly, of course, this is only possible because we are dividing it by n. Okay, so it is of course only since we, in all these definitions, the convergent sequences are used. So primarily sequences are used. When sequences are used, it is not possible to have an uncountable set. Okay. So we know that for uncountable thing, there are tools, but they are not sequences. They come from higher topology. They are called nets. Okay, so of course it is only because it is accountable we can define it. If it was uncountable, then it will be problem, because I will not have any at that I will not have any sequence as such. So all the definitions of densities that are prevalent, they all use sequence.
Thank you, sir. So apart from this talk, I have always a doubt about the irrational number. If you allow me, ask the question about irrational number. May I, sir?
Yeah.
Am I audible, Pranav, sir?
Yes.
Sir, when we talk about the irrational number, we always discuss the E number, which is in between 2 and 3. Then we talk about the beautiful pi and the root square root of some prime numbers, and that's all. Is there means a different type of irrational number that we can
No,
means,
there are lots of irrational numbers. We actually know very few irrational numbers. Most of the irrational numbers we actually do not know at all. For
yeah,
something like say the pi power pi, something
yeah,
like that. There are very so these numbers, there is a branching number theory that deals with these types of numbers, that is called transcendental number theory.
yeah.
So actually we do not know about irrational numbers. Frankly, we do not know about much irrational numbers. So,
So it is it one of reason that means we are not know much more about irrational number. Is it reason that we are always unable to find some bijection type mapping between natural number and irrational number? Is it one of reasons, sir? I know irrational number is uncountable set and all that.
yes, everything. No, actually, for the what happens is that when we work, particularly for the calculation purpose, irrational numbers are not that much needed, because theoretically I know that for every irrational number there is a sequence of rational numbers converging to that irrational number. So we just take a rational number which is very close to it. So in some sense, except for the specialists who are, I said about specialists working in transcendental number theory. Others are not that much concerned about individual irrational numbers. So if we know that the class of irrational numbers have some certain properties, that is sufficient for us. So transcendental number theory, they try to understand individual irrational numbers. That is not that is actually not needed also in that sense in many parts of, in most of the other parts of mathematics. Okay, I think Harshit, yeah, I think I should leave now. Okay.
Ji, sir. Thank you so much. Thank you, sir. Tanya, let's conclude it here now.
As we come to the verge of the event, I, Tanya Singh, on behalf of the Mathematics Department, Kamala Nehru College, formulate my most sincere gratitude to our Speaker of Honor, Professor Pratulananada, for such a wonderful speech and for making us comprehend the essence and natural density function. Great thanks to our teacher conveners for organizing such a significant lecture. Further, I am extremely pleased to the students who have been great listeners throughout the event. Departing the lecture by a quote, only those who will risk going too far can find out how far one can go. Thank you.
Thank you so much, sir, for such a wonderful talk, and especially the Paul Rudolph's result that you have introduced to us. It's really very fortunate to be with you.
Thank you, sir.
Thank you.
Yeah, thank you very much.
Thank you so much, sir.
So, Divya ma'am, can we end this session here, and we will meet in the corresponding events? Your mic is off, I think.
The first event is at 11 now.
I think
Yes,
so.
ma'am. Yes,
Yeah,
ma'am.
so we have about 15 minutes. Get refreshed, have a cup of coffee or tea, and then start.
Then we'll meet again. अच्छा individual event के लिए ना link share कर देना ग्रुप में.